Okay, Year 11, welcome to the Combined Science Physics Foundation Paper 2 Masterclass. Make sure you're looking at the right video or you're in the right room, otherwise you might miss bits and pieces that are for you. So just like the first one, we're going to have two types of slide. We're going to have red slides where you're listening and reading and you're a lot of the time you're going to be finding mistakes. And then green slides where you're reflecting, you're writing, you might be talking to the person next to you and you're fixing the mistakes. The only thing you're going to need is a pen and a paper, or a whiteboard and whiteboard pen, just something you can jot down ideas on. Okay, it's the only thing you're going to need. Okay, so let's jump in. So first thing we'll look at is the required practicals. Now this first one is about forces in motion. I think this is the practical that will come up. I'm not sure about that, but that's the one I think it is. That's what it says in my gut. Okay, and looking at the past papers and how long it will go it last came up, I think this has got a good chance coming up. Okay, so on this page I've got a setup with a trolley and I've got different spaced lines here. I've got a pulley and I've got a weight system and I've got another setup, okay, where I've got light gates, a string and a bench pulley. Okay, I'd like you to think about what is the job of each piece of equipment, why is it there, what's it there to do, and try and jot down a method. You can write a method for either setups, okay, but jot down what you're going to measure and what pieces of equipment you're going to measure it with. Okay, you're going to need to figure out how you're going to change the force pulling the trolley and how you're going to measure the acceleration. That's the key bit in this bit of the experiment. Okay, so jot down what are the pieces of equipment and what they're used for, and try and write a little short method, just bullet points, on how you would actually get a changing force to find out how that changing force affects the acceleration. Okay, pause the video here. Okay, moving on. So this first experiment with the lines, if we know the spacing of the lines and we know how long it takes for the car to go past each line, so we could use a stopwatch to measure that, or you could use a phone or a video camera to record it, we can work out the speed that's going through each of these sections. And if we know the speed going through each section, we can work out the change in speed. And if we know the change in speed and we know how long it takes for it to change speed, we can work out the acceleration. Okay, so we know that if this is 10 centimeters across and we can work out how its speed is, if it went across in a second we can work out its speed, and we can work out how the speed changes here. It might have got faster, I'd imagine so, and we can work out the acceleration. It's quite long-winded, it's not particularly accurate, but you don't need any complicated equipment to measure that acceleration that way. Okay, we'd be changing the force by adding more and more mass to this weight hanger. Okay, so when we add mass to this, it's going to have an effect of pulling, because the mass will have weight, pulling down on this string, which is connected to the pulley, which is connected to the trolley. Okay. The other method, okay, isn't limited by reaction time. So if we're doing this first method, using the lines, you can be limited by how quickly and how accurately you can push that start-stop button if we're using a stopwatch to measure that time. Light gates measure it automatically, so it's not limited by that human reaction time. It works in a really similar way. The card blocks out the light in the light gate and that turns on and off a switch, and we can use that information to calculate acceleration. Both methods will work. Okay, you can increase, just like here, we can change how much weight is added to the weight puller, and we can see what is that effect. Okay, now what is complicated is that one of the things that you've got to keep the same if we're changing the force to see if it's got an effect on acceleration is we need to keep the mass the same. Okay, so to do that, notice we've got weight in the car. Okay, so what we'll do is we'll take mass from the car and add it to the weight hanger to keep the weight pulling on the trolley. Okay, change that weight pulling on the trolley, but keep the total mass or accelerating the same. Okay, so be careful of that. Okay, so we need to make sure that mass is our control variable and the total mass stays the same. If we just add extra masses to the weight hanger, we're increasing the mass of the system, which is going to affect our results. Okay, talking about our results. Our next job is going to be to try and sketch a graph of force and acceleration and mass and acceleration. What happens to the acceleration when I increase the force? What happens to the mass when I increase, what happens to the acceleration when I increase the mass? Okay, and what does it tell us? What's the relationship? What's going on? Okay, so pause the video here. Okay, moving on. We've got, in the first instance, as we increase force, acceleration increases. Acceleration is directly proportional to force. Force is directly proportional to acceleration. It's a straight line, it goes through the origin, it goes through zero. Whereas with mass, it's inversely proportional. As the mass increases, the acceleration decreases. Okay, it's a curve. Now remember, when you're asked to draw a line of best fit, it could be a straight line if that's the pattern, but it could also be a curved line. You don't always have to use a ruler to draw a line of best fit. Okay, you need to choose based on the pattern. Okay, right, moving on. Next practical is about Hooke's law. Okay, and this one, the most common misconception is making length be the same as extension. Length is not extension. They are different things. So your first job, I'd like you to try and jot down, how would you accurately measure the extension of a spring as you change how much force is applied to it? Okay, so how can we find that extension? Pause the video here. Okay, moving on. So this one's quite tricky. Okay, so the length of the spring is going to change in the experiment, and the extension is going to change in the experiment. But if you look at this first case where we don't have any applied force, the extension, it's not being extended. That's the length of the spring. Okay, the original length. Okay, we had to make it bigger, to stretch it out, we add a bit of force, okay, and the length will get bigger. So to find the extension, we take the final length, our measurement, and we subtract the original length from it. Okay, now there are a number of ways you can do that. Just hold a ruler up next to the spring, will get the job done. The best way is to add some kind of pointer to the system. Okay, attach it to the spring, that will point to where your scale is, your ruler. Okay, when you do that, it's a little bit more accurate in finding out that difference in length, which can allow you to find that extension. Okay, next, moving on to our results. What are our results going to look like? If we have force and extension on our graph, okay, and we stretch a spring, what's it going to look like? In your sketch, I want you to try and describe the relationship, and I want you to try and annotate, or try and write down where the limit of proportionality is, or the elastic limit. Okay, think about what a stiffer spring might look like in your graph, or a spring that's not quite as strong. Okay, pause the video here. Okay, moving on. So, in this case, we've got extension along the bottom and force up the y-axis. The first section is linear. This is where Hooke's law is obeyed. It's directly proportional. It's a straight line. It goes to zero. When it gets the limit of proportionality, it stops being linear. It goes curved. It's no longer directly proportional. Okay. The first section, if I release the force, it's going to go back to its original shape. Okay. At any point along this linear section, it will go back to its original shape once the force is removed. Where we've got this limit of proportionality, after that section, it's past its elastic limit. When we release the force, it's going to be permanently deformed. Okay, so you might remember when we did this in lessons, when you got the springs out, if you put too much weight on the end of the spring, and you gave it back to your teacher, it was all stretched out, okay, and it wouldn't go back to its original shape. Now, something you've got to be really careful about in springs and Hooke's law is the axes they give you on the graphs. Okay, so this one has force on the y-axis and extension on the x-axis, but that's not always the case. Okay, sometimes it switches it. Okay, now they do this, they put force on the y-axis just to make the maths a little bit easier. So the spring constant of a spring is the change in the force divided by the change in the extension, or the gradient of this graph. Okay, so this Hooke's law region, we can find out what that spring constant is just by dividing a change in force by a change in extension. You have to do a little bit more maths if you were to get it from this graph, where we've got force along the bottom and extension in the y-axis. People plot this graph because the thing that we're changing, okay, our independent variable, is the load, is the force acting on the spring. Okay, the thing we're measuring to see if it changes is the extension. That's our dependent variable. Okay, so you need to be really careful about the axes they give us. The other thing you need to be careful of are the units. This would be a really common place for the exam board to stick in a unit in centimetres instead of metres, or even millimetres instead of metres. So you need to be really careful about what units you use when we're doing these questions. Okay? The other thing that makes this a bit tricky is that this is a good place to link back with paper 1 content. Now in paper 2, you can be asked questions that involve energy changes. So a common one would be asking about the energy stored in a spring during one of these practicals. Okay, and remember it's the area under the graph is equal to the energy stored in that spring. Okay, moving on. Next one is about waves. Okay, you need to tell me which surface will give out the most infrared energy and what will the bar chart look like. We've got matte black, matte white, shiny black and shiny silver. We've put in hot water. We've put in water of 90 degrees into this Leslie cube and we're going to measure the infrared radiation given out. Okay, pause the video here. Okay, moving on. So, the matte black surface emits the most infrared radiation. The shiny silver will give out the least. And we can tell that by the position of where this infrared detector is. Now, if we want to make this result fair, we need to make sure that the distance from the surface to the detector is constant. We don't want to vary that going from different sides. We also want to do the experiment pretty quickly because the temperature of the water is always going to be going down in this experiment, okay, until it reaches room temperature, because it's giving out lots of infrared radiation, because it's hot and the room temperature is much colder, so it's not absorbing that much. Okay. Now, a different way we can do it is by using different painted cans. You can have a painted black can, a white can, and a shiny metal can. You have a kettle that we can heat with water, we can have a stopwatch, and we can have a thermometer. Okay, how would you go about using these bits of equipment? How would you use these pieces of equipment to generate a method? Okay, I'm going to give you a little bit of help. I'm going to write a method and I'd like you to try and fill in the different parts. Okay, so I'd like you to pause the video here, read the paragraphs, try and fill in the missing words. Okay, moving on. So, with a little risk assessment, we'll go through that first. The biggest hazard in this experiment is the hot water. The hazard is the thing that is dangerous. The risk is what it could cause. It can cause burns. Okay? To reduce that chance of getting burnt, don't overfill the kettle. Carry out the experiment while standing. Wipe up spills. Okay, pour the hot water into the cans while they're on the table. Don't lift them up when you're doing it. Or things like that. Now, in terms of the experiment, we want to fill the metal cans up with hot water. The same volume in each can, so 200 millilitres. Okay, that way we can make sure that the temperature starts at the same point. So it's got the same initial temperature. And then we will record the temperature and measure it at regular intervals, like every 30 seconds, maybe every 60 seconds. Okay, and do this over the course of 10 minutes. Okay, and if we do that, we'll get a set of results that look a little bit like this. Okay, now from this set of results, where we've got temperature on the y-axis and time along in minutes, and we've got silver, white, dull grey and black, I'd like you to say, is it a good emitter of infrared radiation or a poor emitter of infrared radiation? Okay, good or bad? Pause the video here. Okay, that shouldn't have taken too long. So, to tell us if it's a good or a bad emitter, it's how quickly the temperature drops. If the temperature drops really quickly, that means it's going to be giving out lots and lots of infrared radiation. Okay, so the black surface is the best emitter of infrared radiation out of these four. It cools the fastest. The silver is the worst. It cools the slowest. Its temperature drop isn't as quick, isn't as rapid. Okay. The other way we can investigate this is not just by looking at emission of infrared radiation, we can look at absorption. So in this experiment, we can have a heater in the middle that gives out infrared radiation, okay, like a toaster. And we can have two different surfaces. We can have shiny surface and a matte black surface, and it's stuck on with candle wax. Okay? I'd like you to tell me, just jot down, what's going to happen when the heater is turned on. Okay? And using that information, which surface is the best at reflecting heat energy or infrared radiation? Which surface is the best at absorbing heat energy or infrared radiation? And why should the plates be the same distance from the heater? Okay, pause the video here. Okay, moving on. The shiny surface is the best reflector. Okay, I know that because it took longer for the wax to melt and the coin to drop. The matte black surface is the best at absorbing infrared radiation. I know that because it took a shorter amount of time for its temperature to rise so that the wax melts. The plate should be at the same distance so they get the same intensity of infrared radiation. The further you away from that infrared source, the less infrared radiation you will be getting. It will be spread out. Okay? Right, moving on. Vectors and scalars. I would like you to try and jot down as many different vectors and scalars as you can. Pause the video here. Okay. Now, this is a really common opening question. So things where you can just do little tick boxes or write down a couple of keywords or circle the words. We've got scalars and vectors. These are all things that only have a size or an amount, or the best word, a magnitude. Scalars only have this amount, okay? Whereas vectors, they have the amount, but they also have a direction. So vectors come with a direction, scalars do not, okay? Moving on, I'd like you to jot down, describe the journeys, describe the motion that's happening in each of these 6 graphs. Okay, what's happening in each graph? Pause the video. Okay, moving on. The first graph, distance time graph, the distance isn't increasing and it's not decreasing. The thing is stopped. The second graph, the distance is increasing and it's a straight line, so it's at a constant speed. This graph, the third one, the distance is decreasing. It's at a constant speed because it's a straight line, and it's going back to the start. The distance is decreasing. Okay. This third graph at the bottom, sorry, the fourth graph, the distance is increasing. Okay, so it's moving, but it's not a straight line. This one shows acceleration. Okay, it's not a straight line. Distance time graph, not a straight line, is accelerating. Okay, the speed is getting quicker and quicker and quicker because the gradient, the slope is getting bigger and bigger. This one, it's decelerating. At the beginning, we've got quite a steep slope, and at the end, it's getting flatter and flatter. So it starts off fast and then it gets slow. So this one shows deceleration. Okay, this last graph is constant speed because it's a straight line, but it's moving slower than this than this one in the middle, because it's got a lower gradient. Next, you need to be careful. You need to describe what's happening in each graph. It's different. Notice it's velocity, not distance. Velocity. This first one is not stopped. Okay, so I'd like you to try and describe the motion in these new graphs. They are different. They are all different. Okay, so pause the video. See what you can do. Describe each graph. Okay, moving on. So, for this first graph, the velocity doesn't get bigger, doesn't get smaller. Its velocity doesn't change. It's going at a constant velocity. The next one, the velocity is increasing. It's getting bigger and bigger and bigger. Okay, that means it's accelerating at a constant rate. This one, the velocity is decreasing. Okay, it's decreasing at a constant rate because it's a straight line. The velocity is getting smaller. Here, we've got increasing acceleration. It starts off, okay, the change isn't very much, and then to the end, the slope gets really big, so the acceleration is increasing. Here, we've got decreasing acceleration. We start off with a rapid change in velocity, and then as we go on in time, it gets slower and it gets a smaller change and a smaller change and a smaller change. It's not getting slower. The acceleration is getting smaller. Okay, then the last graph, we've got constant rate acceleration because it's a straight line, but it's not accelerating as quickly as B. Okay, it's not a steeper graph. Okay, putting some of those ideas together, I think is one of the more challenging areas in paper 2. It's all about terminal velocity. Okay, this shows a description of a speed time graph in terms of forces and acceleration to a parachutist. Okay, I'd like you to try and describe what might be happening in terms of the forces as somebody jumps out of a plane. What are the forces involved? How do they change? Okay, what direction do they act? What will be the resultant force at different parts of the graph? Okay, so pause the video here, try and jot down your thoughts. Maybe jot down a picture showing the resultant forces. Okay, so pause the video here. Okay, moving on. So the important thing about terminal velocity is that the drag force, the air resistance in this case, is changing based on the speed and the surface area. So at the beginning, weight is bigger than the drag force, so it accelerates. Then, because we're getting faster, the drag force increases and we don't accelerate quite as much. And then we get to a point where the drag force equals the weight, so we stop accelerating. We reach a terminal velocity, a constant velocity. Then it all changes when the parachute is opened. Okay, the air resistance increases dramatically because it's a much bigger surface area, so it slows down, it decelerates until we reach a new terminal velocity. Now, sometimes AQA can be quite tricksy and they ask terminal velocity questions, but they don't talk about a parachutist. They'll talk about, I don't know, a car driving at with a constant thrust getting a top speed. Or they'll talk about a ball bearing falling through some soap. Okay? So long as there's some sort of drag force based on the velocity, okay, and it reaches a constant speed, the question is most likely going to be about terminal velocity. Okay, so be ready to use that phrase, terminal velocity, when the resultant force is zero between the thrust force and the drag force. Right, next, we've got Newton's laws. I'd like you to try and fill in the missing words that describe Newton's laws of motion. Pause the video here. Okay, moving on. So the first law, if the resultant force on an object is zero, then the object will stay stopped or continue to move at a constant velocity. For the second law, force is mass times acceleration. If the resultant force acting on an object is increased, then its acceleration will increase. If the mass of the object is lowered, the acceleration will be increased. Okay, so careful of this ones, they work backwards. Third law, according to Newton's third law, whenever two objects interact, they exert equal and opposite forces on each other. So we've got a satellite in the Earth. This green force is that attraction due to gravity. Okay, be careful, sometimes it's difficult to label up where those pairs of forces are. Okay, right. Next thing I'd like to do is start to do some fix it the mistakes questions. Okay, we need to fix the mistakes. We've got a swimmer swimming along and we've got some answers here. I'd like you to figure out how many marks they get and what would you do to improve their answer. Okay, try and make it better. Pause the video here. Okay, moving on. Not a great answer. Okay, but this is a really easy answer to write down. Okay, the man is stopped. Okay, the student is going to think that because the force A and force B are equal, the person must be stopped. That is not true. A resultant force of zero does not mean stopped. It means they're not accelerating. Okay, that's the key thing. So they're moving at a constant speed. Okay, so we're moving at a constant speed. Then this question becomes a little bit easier because this question is really about terminal velocity. This swimmer has sort of reached a terminal velocity, a top speed caused by the massive amount of forward thrust they can get from their arms and their legs, balancing with the drag force caused by them trying to get through all the water and bumping into the particles in the water. Okay, so you need to basically describe what terminal velocity is. So we've got the man will accelerate. This causes force B to increase until it equals force A. The man will move at a higher constant velocity. Okay, it's like taking off the parachute, okay, after you've jumped out of a plane. So, as I say, terminal velocity is not always about a parachute and a skydiver. It can be anything in which an object is moving through a fluid, so a gas or a liquid, where drag increases with speed. Right, next thing, stopping distance. I like to try and fill in the missing words. Okay, so we've got the thinking distance equals the distance travelled in the time it takes the driver to react to a hazard. When you're describing stopping distances and braking distances and thinking distances, use the word distance. The distance travelled while. The distance. Okay? Be really careful in the language you use or you might drop lots of marks. Okay? The braking distance is the distance travelled while the brakes are applied till the car stops. Okay? Here we've got a graph. We've got the red bars showing thinking distance, the blue bars showing braking distance. As speed increases, both increase. I would like you to try and jot down a list of things that affect thinking distance and affect braking distance. And for each of them, I want you to be really careful. Think about how it affects it. Is it increasing the thinking distance or decreasing the thinking distance? Okay, so don't just write down alcohol. Alcohol is going to affect the thinking distance, but if I consume alcohol, it will increase my thinking distance. It will increase the distance I travel while reacting to a hazard. Okay, so jot down some ideas. Pause the video here. Okay, here are some different examples. We've got alcohol, we've got speed, the speed of the car, we've got name distraction, so phones, radio, age, tiredness. But when you're answering questions about this, be really careful about how it's affecting. Is it increasing or decreasing? All of these things, okay, alcohol, the name, distraction, age, tiredness, they're going to affect your reaction time. Okay, speed doesn't directly affect the reaction time, but if you're traveling faster, you're going to travel a greater distance while you are reacting. So your thinking distance will be increased if you are traveling faster. Braking distance, we've got mass of the car, speed again, age of the brakes, quality of the tyres, road conditions. Don't say weather. As tempting as it is to think about weather, be more specific. Say the road conditions, it's wet, it is icy. Okay, things that increase the braking distance or affect the braking distance is anything that will change friction or anything that will increase or decrease the kinetic energy of the car. Okay, so you've got a bigger mass of a car, it will take more energy, you have to transfer more energy out of the kinetic energy store to slow it down and make it stop. Okay, right, moving on. We've got to find the mistake and fix it. Okay, we've got this question about forces. Where do they go wrong? Where have they gone right? Find the mistake and fix it and pause. Okay, moving on. So they've got some marks. They've got the right idea. So they're timesing these two numbers together. Okay. But they've not got the right answer. Now this question, they've got the right idea. It is directly proportional because it's a straight line and it goes through 0. Okay. But here, they just didn't write down a 0. They didn't copy the number from their calculator accurately. Okay. This is something that if you have a little bit of time left over at the end of your experiment, the end of your exam, check that. For each calculation, try and just do it again on the calculator and see if you get the right number, because you might have just forgotten to write down a 0 and that'll drop you a mark. And then the unit for work done, unit for energy, is joules, not watts. Okay? Right, moving on. Magnetic fields. Magnetic fields can be mapped out using small plotting compasses. I'd like you to try and jot down how you could find the fields around a bar magnet. What are the missing words? Pause the video here. Okay, moving on. So missing words, we've got place the plotting compass near the magnet on a piece of paper, mark the direction of the compass needle where it points, move the plotting compass to many different positions in the magnetic field, marking the needle direction each time, join the points together to show the field. Remember, the field will go from north towards south. From north to south. You could use iron filings to show the shape of the field, but it doesn't show the direction. You need a plotting compass to find the direction. Okay. We've got a question about magnets. The paper clip in figure 2 is not a permanent magnet. You need to describe, okay, you need to explain what would happen if the paper clip was removed and brought close to the south pole of the permanent magnet. Okay. So find and fix the mistake. Okay, moving on. This answer gets no marks correct. No marks. Okay. To get our marks, we'd say the paperclip would be attracted to the new magnet because of induced magnetism. Okay, as soon as I remove it from the magnetic field, it won't be a permanent magnet anymore. So it's an induced magnet, which will mean it's always attracted to the actual permanent magnet. Okay. You need to be able to find the direction of a field around a wire. If we've got current flowing up through the page, we go in this direction. If we've got it down through the page, we go in the opposite direction. We can use the right hand grip rule to find that. Okay. So I'd like you to try and fill in the missing words. And moving on. So when a current flows in a wire, it creates a circular magnetic field around the wire. This magnetic field can deflect the needle of a compass. The strength of the magnetic field is greater the closer you are to a wire. Okay, so if you want a bigger magnetic field, you want to go close to the wire, or you want to increase the current flowing through it. Next, EM spectrum, you need to know the order, and you need to know some of the uses and the dangers. Okay, so what I'd like you to do, think about the song. I'm not going to sing it on here, but think about the song. Put them in order, from long wavelength to short wavelength, and try and give a danger for each. Which is the most dangerous? Pause the video here. Okay, moving on. Hopefully, you've got them in the right order. We've got radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-ray, gamma rays. Okay, we've got low energy with long wavelength and low frequency. We've got high energy with short wavelength and high frequency. The most dangerous section is the high energy side. This is ionizing radiation. This can lead to cancer. Okay, so I've got my dangers and my uses. So microwaves can cause internal tissue burns. Infrared can cause skin burns. The microwaves can penetrate through into tissue and cause internal heating, whereas infrared will just burn the surface. Okay. Ultraviolet X-rays and gamma rays, they're ionizing, and I say they can cause cancer. Okay. Now, that's my last slide. I wish you the very best of luck. I'm sure you're going to do absolutely fantastically well. I hope to see you after the exam, and you can tell me how it's all gone. Best of luck. Take care, Year 11. Bye-bye.